Hello. So camera on. So let's start. Let me start sharing the screen. Okay, last time हमने किया था separable normal linear spaces. तो separable तो तुम्हें पता ही है topological space में वही definition यहाँ पर भी है, that it has a countable dense set. But we have got a linear structure here, so that should make things different because linear structure does affect. It does interact with the metric structure or the topological structure of a normal linear space. So मैंने कल कहा था LP if P as a theorem use
सर आपकी आवाज नहीं आ रही है।
अब आ रही है आवाज हेलो
जी सर आ रही है
ना वही ओके लेट मी रीस्टार्ट तो मैं कह रहा था कि LP is separable okay for P lying between greater than or equal to 1 but less than infinity, and you know what do we mean? We mean Pth power summable sequences by LP. We mean all scalar sequences x1 x2 such that xi belongs to k and summation xi raised to power p I runs from 1 to infinity is less than infinity. So we're going to show that LP is separable. Proof. Now I just have to recall it. Okay, let me see. Proof. Proof here होगा इसका consider the set. We have to show that it has a countable dense set. So we have to show that let's consider this set M equal to union n runs from 1 to infinity Mn, where Mn is equal to the sequences of this type y1, y2 up to yn. उसके बाद 0, 0, 0, 0 such that yi belong to q. ऐसी sequences which have got only finitely many terms and they belong to YQ. Clearly, Clearly, Mn is a countable set because rationals are countable for all n, and hence M is a countable set. It's a countable union of countable sets. तो Mn countable होगा? Of course Mn countable. अगर मैं M1 लूंगा, M1 का मतलब ऐसी सीक्वेंसेस नहीं इस टाइप का Y1 फिर उसके बाद 0 0 0 yi's are rationals. So ये तो इतनी ही सीक्वेंसेस होंगी जितने रैशनल नंबर्स, क्योंकि बाकी सारे जो इसके कोऑर्डिनेट्स या जो इसकी टर्म्स हैं वो फिक्स्ड है. So M1 is countable. How about M2? M2 would be of the type Y1 Y2 उसके बाद 0 0 0 and Yj belongs to the rational numbers. So अगर मैं Y1 को फिक्स करूं और Y2 को रन करूं, I will get a countable set. ठीक है ना? So for each Y1 it's a countable set. And how many Yi's are there? As many as rational numbers. So it's a countable union of countable sets, therefore countable. So you can go on and on. So all Mn's are countable. And because M अगर मैं लेता हूँ union n runs from 1 to infinity, it's then a countable union of countable sets, and hence M is countable because Yi's are rational. Okay. Now we show that M closure is equal to LP. ठीक है, हम दिखाएंगे ये अगर मैंने दिखा दिया तो इसका मतलब it is the closure of a countable set, then LP जो होगा it would be a separable space. Okay, we show that. So let xn x equal to x1 x2 belong to LP. यहाँ पर मैं थोड़ा लूंगा xi's are real numbers, where xi's are real numbers. थोड़ा सा इसमें एडजस्ट करना है. Now it's pth power summable sequences. Therefore, for each n, for each epsilon positive, there should exist a natural number n belonging to the set of natural numbers such that summation I runs from n plus 1 to infinity mod xi raised to power p is less than epsilon, anything actually, epsilon, should I write it? चलो मैं लिखता हूँ यहाँ पे epsilon by 2, but it could be epsilon raised to power p by 2, but वो हम adjust कर सकते हैं because the tail of a convergent series can be made arbitrarily small. After a certain stage, the sum of terms, if a series is convergent, has to be very, very small, arbitrarily small. Only then would the series converge. So because this is a convergent series, why? Because this belongs to LP, pth power summable sequence, means this sum means this converges, this is less than infinity. जो ना मैंने यहाँ इसकी definition नहीं है. Alhamdulillah. So this can be made arbitrarily small. Okay, now also for each xi, belonging to R, there exists yi belonging to Q. Now since since Q closure is equal to R, that is mod of xi minus yi is less than what? Any number, there would exist, this could be made less than epsilon, I don't know, epsilon raised by p by 2. चलो इसको हम बाद में एडजस्ट कर सकते हैं. So this can be made arbitrarily small because Q closure is equal to R. Then norm of X minus Y as a sequence P is equal to summation I runs from 1 to infinity xi minus yi raised power p. चलो मैं यहाँ इसको p to power यहाँ कर देता हूँ just to make it easier. चलो अगर तुम्हें पसंद नहीं है तो पहले मैं यहाँ ऐसे लिख देता हूँ, फिर मैं लिखूंगा norm of x minus yi this p whole raised power p is can be written as summation I runs from 1 to n xi minus yi raised power p plus summation I runs from n plus 1 to infinity xi minus, इसके बाद तो ये 0 है ना, y, so it is just xi, actually होना चाहिए xi minus 0 क्योंकि after n yi's are 0, so that is equal to summation I runs from 1 to n xi minus yi raised power p plus summation I runs from 1 to n plus 1 infinity xi raised power p, sorry. तो अगर ऐसा है तो व्हाट डज इट मीन, अब मुझे वही सोचना है कि ये बन जाए लेस देन एप्सिलॉन, है ना. सो तो मैं यहाँ ऐसे कर सकता था, इसको मैं लेस देन एप्सिलॉन, यू नो, सो आई वांट टू मेक इट व्हाट लेस देन एप्सिलॉन. तो वही मैं कह रहा था, हमें यहाँ एडजस्ट करना पड़ेगा. मुझे पता नहीं मैंने इसको लिया है एप्सिलॉन बाई 2, सो दिस इज लेस देन एप्सिलॉन बाई 2. अब हमें अकॉर्डिंगली इसको ठीक करना है. तो मैं यहाँ पर जो है ताकि ये बन जाए, मैंने दिस इज एप्सिलॉन बाई 2, तो मैं चाहता हूँ ये बन जाए, इसको मैं ऐसे एडजस्ट करूँ ताकि ये बन जाए लेस देन एप्सिलॉन बाई 2. तो कैसे करेंगे, तो मुझे यहाँ n होना चाहिए, क्योंकि जब मैं इसको n टाइम्स एप्सिलॉन बाई 2 तो शुड बी, चलो कोई बात नहीं, वो हम देख सकते हैं यहाँ पे क्या होना चाहिए. एप्सिलॉन बाई 2n अगर मैं लेता हूँ, क्योंकि मैं इसको एडजस्ट कर सकता हूँ बिकॉज दे आर आर्बिट्रली क्लोज. तो अगर मैं इसको लेता हूँ एप्सिलॉन बाई 2 एप्सिलॉन बाई 2n कर देते हैं, ठीक है. So let's make it epsilon by 2n. So this is n times epsilon by 2n by first, चलो इसका नाम कुछ देते हैं स्टार, by double star and star. चलो इसको स्टार कह देते हैं. So that's equal to epsilon. It implies that norm of x minus y p is less than epsilon by p, where epsilon is arbitrary, which implies that M closure is indeed, because for every x belonging to LP, I have been able to find some y belonging to this countable set such that the norm between them is arbitrarily small. So therefore, it implies that x belongs to M closure. So which implies that LP is contained in M closure, and of course M closure तो है ही LP में, क्योंकि वो सभी summable sequences है, P to power summable, and या सीधे लिखते हैं, and since M closure is contained inside LP, so therefore LP is separable, and hence क्या हो गया, LP is separable for all P greater than equal to 1 but less than infinity. अब इसमें होम असाइनमेंट तुम्हारा है जो छोटा सा ही है, कहीं से भी मिल जाएगा अगर तुम ढूंढो तो. L infinity is not separable. So this was about separable spaces. So L1, L2, L3 सभी ये जो summable sequences है, P to power summable, they are all separable. But L infinity is not, जो कि तुम चेक कर सकते हो by a simple ज्यादा कुछ करना नहीं है. So okay, we may move ahead and do another theorem about separability. Separability tells us again about something about the size of a space. जिस तरह से reflexivity का भी वैसा ही कुछ है. It has a definition, proper definition, and all that. We can intuitively it tells us that space is somewhat smaller. So now what we do with your theorem, let's do it. वो ये है कि एक theorem करते हैं. Where if X is a normal linear space, is a normal linear space, then X star उसका dual अगर separable है, it implies that X is separable. Converse is not true. अगर X separable है तो ये जरूरी नहीं है कि X star separable हो, लेकिन अगर X star dual separable है तो space भी separable होगी. Separable means it will have a countable dense subset. So let's do the proof. उसके बाद हम देखेंगे converse क्यों true नहीं. So let, तो अब चूंकि X star separable है तो उसमें एक countable dense set होगा जिसको हम list कर सकते हैं. Countable means we can write it down as a list. So F1, F2, so on and so forth, be a countable dense subset of X star. तो मैंने एक countable set मान लिया. Then for each n, we can choose, तो हम एक xn choose कर सकते हैं belonging to x with norm of xn equal to 1 and fn at xn greater than equal to 1/2 of norm of fn. ठीक है, तो हम एक xn ऐसा ढूंढ सकते हैं, क्योंकि सपोज ऐसा नहीं है, मैं कह रहा हूं कि fn चूंकि एक बाउंडेड लीनियर फंक्शनल है तो मैं ऐसा हमेशा चूज कर सकता हूं, ऐसा कोई वेक्टर सच दैट दिस इनइक्वालिटी इज ट्रू फॉर इफ. लेकिन अगर ऐसा नहीं है फॉर अदरवाइज, अगर कोई ऐसा एग्जिस्ट ही नहीं करता, यानी अदरवाइज फॉर अदरवाइज इफ फॉर एवरी x with norm x equal to 1, अगर reverse is true, if fn of x is less than 1/2 norm of fn, it would imply that taking the supremum, अगर सभी के लिए true है तो it would mean norm of fn is less than 1/2 norm of fn, which is absurd because it implies that 2 is less than 1, which is absurd. इसका मतलब कोई ना कोई ऐसा वेक्टर होना चाहिए for each n such that this is greater than equal to 1/2. So मैंने उसका नाम रखा, क्योंकि f1 के लिए भी होना चाहिए, f2 के लिए भी होना चाहिए ऐसा वेक्टर. जो f1 के लिए है उसका नाम मैंने रखा x1, जो f2 के लिए मुझे मिलेगा उसका नाम होगा f2, x2. Similarly, in this way I have a countable set of vectors in x. So in this way या सीधे ही लिख देते हैं, let y be equal to, अब मुझे मिल गया एक वेक्टर span of x1, x2, मैंने इन सभी का स्पैन लिया और along with the limit points, यानी क्लोजर उसका लिया मैंने. ठीक है, so तो I have got now a countable set inside x. Okay, now we claim that, तो मुझे मिले हैं xn, I have found an xn inside x which is a countable set. I have to show that x is separable, right? For the time being, I show that जो x है, या चलो x is equal to y, which is equal to span of x1, x2 का क्लोजर. तो फिर हम दिखाएंगे ये जो नीचे सेट है इट इज इंडीड काउंटेबल। देखो x1 x2 काउंटेबल है तो उनका स्पैन काउंटेबल होना चाहिए जो हम बताएं। तो पहले हम इतना तो प्रूव कर ले, ये हमारा क्लेम है y is equal to x फॉर इफ मान लो x y के बराबर नहीं है, then y is a proper closed, क्योंकि क्लोजर है किसी सेट का, सबस्पेस बिकॉज स्पैन है ऑफ x, hence by Han-Banach theorem. By Han-Banach theorem, ठीक है। बिफोर यूजिंग Han-Banach theorem पहले हम एक चीज और करते हैं। अगर ये इसका प्रॉपर सबस्पेस है, क्लोज सबस्पेस है, we fix some a, हम एक a which does not belong to y, क्योंकि प्रॉपर सबस्पेस तो एक एलिमेंट होगा, ढूंढ ही सकते हैं हम, लेकिन हम ये ऐसा ढूंढ सकते हैं जिसका नॉर्म 1 है। उसकी वजह है सिर्फ if a does not belong to y and y is a subspace, तो पहले तो ये है कि ये जीरो नहीं हो सकता, क्योंकि y में जीरो होता है, अगर वो सबस्पेस एडिटिव आइडेंटिटी तो ये हो नहीं सकती, which implies that then a by norm a भी y में है। यानी मैं मान सकता हूं एक ऐसा वेक्टर मुझे y में मिलेगा जिसका नॉर्म y के बाहर मिलेगा, जिसका नॉर्म 1 है, क्योंकि मुझे जो y के बाहर वेक्टर मिलेगा वो नॉन जीरो होगा, और नॉन जीरो को अगर मैं उसके नॉर्म से डिवाइड करूंगा वो भी y में नहीं होगा, क्योंकि सपोज a by norm a अगर y में है, it could imply a y में है ना, because it's close with respect to scalar multiplication. So I can find this a outside this closed subspace such that its norm is equal to 1. Now, then by Han-Banach theorem, जो कि मैंने पहले लिख दिया था, Han-Banach theorem कहता है we can find an f, हमें f मिलेगा dual में, such that it would kill such that f of y is equal to 0 for all y belonging to y, and f of a is not equal to 0. Okay, actually for every a not belonging to y this is true, in particular for this a which जिसका norm 1 है, I can find this function. ठीक है, now given epsilon positive, now we have to remember f belongs to x star, and x star is separable, and I have got f1 f2 there such that this closure is equal to x star. well, ये मैं कर चुका हूँ, so therefore given any epsilon positive we can find some fn, we can find, we can choose, चलो मैं लिखता हूँ, choose n belonging to the set of natural numbers such that norm of f minus fn is arbitrarily small, it is less than epsilon for any epsilon positive. Now what I do, but if I want to evaluate fn at a, this is clearly less than equal to supremum over norm x equal to 1 fn of x, isn't it? Because norm of a is equal to 1, which is the same thing as norm of fn, and by my choice fn जो है, fn is less than equal to twice, so this is less than equal to twice modulus of fn xn, चाहे तो इसका नाम कुछ रखते हैं यहाँ इक्वेशन का, चलो 1, और यहाँ लिखते हैं by 1, ठीक है। So which can be written as twice fn of xn minus f of xn mod, of course, q, because f of xn is 0, xn belongs to y, all xn's, y is equal to span of these vectors, so they must belong to the y. So, or f kills everything inside y. So f of xn would be 0 for all n. So which would be less than equal to twice norm of, चलो पहले लिख देते हैं, it is equal to twice using the pointwise addition applied to xn, और चूंकि norm of xn is equal to 1 हमने पहले लिया था, तो this is less than equal to twice norm of fn minus f. But अगर मैं इसका नाम second रखूं, so ये जो norm of fn minus f, this is less than twice epsilon by second. ठीक है, so this is, तो हमें मिल गया, let's do it, next page. So that is fn of a in modulus is less than twice epsilon for all n greater than equal to 1. तो हमारा काम हो गया 10 f of a जो है is less than equal to, in the triangle inequality, f of a minus fn of a, right, plus f, मैंने क्या ऐड किया, f of n. This is just triangle inequality, लेकिन ये है यहाँ पे less than 2 epsilon, but this is epsilon. Why? तो reason मैं लिखूंगा fa minus fn of a is less than equal to supremum over norm x equal to 1, because norm of a is equal to 1. F minus fn applied to a, which is the same thing as norm of f minus fn, which by our thing is less than epsilon. So it means that f of a is less than 3 epsilon. And since epsilon is arbitrary, what is a non-negative number that is less than every positive number? कौन सा है? कौन सा ऐसा, क्योंकि ये non-negative number है, which is less than any positive number. कौन सा non-negative number है जो किसी भी positive number से छोटा है? Hello, anybody awake?
Yes sir.
मैंने पूछा कौन सा ऐसा non-negative number है जो हर positive number से छोटा है? जीरो है, और कौन है? तो अगर ये नॉन नेगेटिव नंबर है और हर किसी पॉजिटिव नंबर से छोटा है, तो f of a must be 0, which is a contradiction. Which is a contradiction. So therefore, x is equal to span of the closure of the span of span of x1, x2, so on and so forth. Now consider the span of, consider the all linear combinations of finite linear, वही तो finite ही मतलब है, all linear combinations of x1, x2 with scalars having rational real and imaginary parts, having rational real and imaginary parts. Then this set is dense in span. But this set is countable. This set is countable. Let's call it A. चलो ए चलो ए लिखते हैं. So and A closure is equal to span of x1, x2, so on and so forth. And A closure, ठीक है ना? So A closure is span of this thing. So A closure का closure is again A closure, which is the same thing as span of x1, x2, so on and so forth, which is equal to x, which means that नहीं मुझे ऐसे लिखना चाहिए, इसको ए क्लोजर पहले लिख लो, डबल क्लोजर बाद में. अब सही, क्योंकि क्लोजर का क्लोजर वो खुद होगा, बिकॉज क्लोज सेट का क्लोजर वो खुद ही होता है सेट. सो therefore x is separable because it is the closure of a countable set, right? I'm taking rationals as its real and imaginary parts. वो तुम खुद कर सकते हो, वो है, मतलब वर्कआउट कर लो, तुम्हें उससे हेल्प मिलेगी. जब मैंने दिखाया था ना वो LP इज सेपरेबल, उसमें जो हमने M सेट दिखाया था वो काउंटेबल है, बिल्कुल वैसा ही कुछ यहाँ पे करना होगा. ओके, so this finishes our this separability के बारे में जो हम कर सकते थे. हाँ, मैंने कहा था अगर x स्टार सेपरेबल है, जो हमने अभी किया, रिमार्क में लिखते हैं converse of the above theorem is not, what should I say, is not true for if we take x equal to L1, then x is separable, जो कि हमने किया था. LP is separable for, but x star is equal to L1 star is equal to L infinity is not separable. So अगर x star separable है तो x हमेशा separable होगा, लेकिन conversely ऐसा हो जरूरी नहीं है. Okay, अब before going to the next thing, I want to talk about, define हम कर सकते हैं what we call weak convergence. Weak convergence हम कर सकते हैं. Let's define first it. Let X be a normal linear space. Normal linear space. Then a sequence X sub n contained inside X is said to converge weakly to X belonging to X if X star at Xn converges to X star at X for all X star belonging to X star. पहले तो ये है कि कन्वर्जेंस जो नॉर्मल कन्वर्जेंस है या जो नॉर्म कन्वर्जेंस है या जो स्ट्रॉन्ग कन्वर्जेंस है, कभी कभी हम उसको बोलते हैं, जो ना हमने अभी पढ़ी, अगर कन्वर्जेंस implies वीक कन्वर्जेंस, अगर कोई सीरीज सीक्वेंस कन्वर्जेंट है इन द नॉर्म, then it must be weakly convergent also. For if Xn converges to X under usual thing, then it means that norm Xn minus X converges to 0. ये हुआ norm usual convergence in a normal linear space. Now X star at Xn minus x. Let me write it like this: x star at xn minus x star at x, using the pointwise addition inside x star, big X star, would be, can be written as x star into xn minus x. But this is a functional, so this should be less than or equal to norm of x star into norm of xn minus x, which goes to 0 as n approaches infinity. तो ये भी 0 हो जाएगा. So this would, now this is true for all x star belonging to x star. तो इसका मतलब हुआ x star at xn converges to x star at x for all x star belonging to x star, which means that xn converges to x weakly. इसको बोलते हैं वीक, इसको ऊपर थोड़ा सा हम wk लिखते हैं, so इसका मतलब ये कन्वर्ज करता है weakly. Similarly, right, converse is not true, and a weak convergence need not imply non-convergence. For example, converse is not true. वैसे इसमें 1 मिनट रह गया है, मुझे लगता है मैं इसको बंद करूंगा, फिर तुम वापस ज्वाइन कर लेना, ठीक है? Everybody have awake? Okay, क्योंकि 1 ही मिनट है तो इसका कोई